All right, so today we're going to talk about, I really should have combed my hair, but that's not what we're going to talk about. We're going to talk about randomness and probability. So stats is about trying to make predictions and using numbers and math to try to figure out stuff. We talked about randomness, but probability is an important part of it too. So we're going to discuss how you need to be random in the sense that because things in life are random, but there's still a mathematical probability of something occurring. And so the whole point of probability is to try to predict an outcome. We could do that based on some stuff we're going to cover today. So random phenomenon is a situation in which we know the outcomes could happen, but we don't know which particular outcome did or will happen. All right. In general, each occasion upon which we observe a random phenomenon is called a trial. So Mr. Adams is going to talk about trials a lot today. If I flip a coin, first time I flip it, it's going to be trial 1. Second time I flip it, trial 2, and so on and so forth, right? Each trial should note the value of the random phenomenon. That's called the outcome. Heads or tails is the outcome. Trial 1, outcome heads. Trial 2, outcome tails, or whatever it is, okay? When we combine outcomes, the resulting combination is called the event. So an event would be something I'm going to flip a quarter 36 times. And then we got to figure out what's the probability that it'll land on heads. Probably 18, right? It could be more, it could be less, but that's how you do the math. A collection of all possible outcomes is called the sample space. Rolling die is a good one. Does anybody know off the top of their head how many possible combinations you could have of rolling 2 6-sided die or dice?
Is it like 50? No?
No, it's not 50.
Is it higher?
It's 36.
Oh.
It's 36, but it depends on how you think of it, because you could roll a 2 on the first die and a 4 on the second die, or you could roll a 4 on the first die and 2 on the second one. So there's some doubling up and stuff. So it depends on how you frame the question, but all the possible outcomes is the sample space, okay? So the law of large numbers, this is a big one. I just saw a movie, or no, it was Ozarks. I was watching Ozarks on Netflix. I was watching it again. The guy that launders the money kept talking about the law of large numbers, which is funny. When thinking about what happens, the combination of outcomes, things are simplified if the individual trials are independent. Roughly speaking, this means that the outcome of one trial shouldn't have an influence or change the other. Flipping a coin is independent. You have a 50-50 shot of flipping heads on a balanced coin. Okay? So when I flip a coin one time, if I get heads, guess what the probability of me flipping heads the next time is? Still 50% chance of getting heads. However, the law of large numbers says that in the long run, there's a relative frequency of repeated independent events gets closer and closer to a single value. So if I flip heads 20 times in a row, and I know that the coin is fair, at some point in time, the law of large numbers will say, hey, you got a 50-50 shot. You're going to get a bunch of tails coming up soon. So even though each time I flip the coin, I've got a 50-50 shot of getting heads or tails, there's this large number thing. Now, this is how card counting schemes work. They keep track of what cards have been played, and then if certain cards have been played, that leaves the certain other cards left in the deck, and when you get to a certain point, it's smarter to bet more money than less money. Okay, we call the single value the probability of the event. Okay, because this definition is based on repeatedly observing the event's outcome, this definition is often called empirical. Empirical is what we see. Okay. The law of large numbers says nothing about short-run behavior. Relative frequencies even out over the long run, and this long run is really long, infinitely long, in fact. So the law of averages that is the outcome of a random event that hasn't occurred in many trials is due to occur doesn't exist at all. So I just countered myself, right? I said if I flip a quarter 20 times in a row, it seems like we might flip tails. Now, if I flip, if it's 50-50, if it's truly 50-50 shot, and I flip a quarter a million times, a half a million times should be heads, a half a million times should be tails. That's the law of large numbers. But because the law of large numbers is infinitely large, I don't know how many quarters are being flipped. I don't know where I'm at in that. I'm looking at the short term. I flipped the quarter 20 times and got heads every time. There could be somebody in another part of the world and they've flipped a quarter 20 times and they've gotten tails every time. So while it seems like I should flip tails because of the law of large numbers, it doesn't necessarily mean that I will. Does that make sense? Okay. So when probability was first studied, a group of French mathematicians looked at games of chance in which all the possible outcomes were equally likely. They developed mathematical models of theoretical probability. So we're going to talk about theoretical probability and empirical. Okay. It's equally likely to get 1 out of 6 outcomes when you roll a fair die. So if I have a die, is the single word for dice, and I roll it, I could roll a 1, I could roll a 2, I could roll a 3, a 4, a 5, and a 6. I got an equal probability of rolling each side. Now, it's equally likely to get a heads or tails if I toss a fair coin. There was a study done, I think on pennies or something a long time ago, and it said there's a slight advantage to getting one over the other, just because of the way the coin was minted. But we're talking like a fraction of a percent. However, keep in mind that events are not always equally likely. A skilled basketball player has a better than 50-50 chance of making a free throw as opposed to somebody that's never played basketball. So this is how we do the math. The probability of an event is the number of outcomes in the event divided by the total number of possible outcomes. Okay? So, for example, I've got a 1 in 6 chance of rolling a 3. How do I know that? Because I know that there's only 1 3, but there's 6 total possible outcomes. I could roll a 1, I could roll a 2, I could roll a 3, I could roll a 4. So we put the 1 up here, and then the 6 down here. In everyday speech, when we express a degree of uncertainty without basing it on long-run relative frequencies or mathematical models, we are stating subjective or personal probabilities. Personal probabilities don't display the kind of consistency that we will need probabilities to have. So we'll stick to the formally defined probabilities. Okay. There are 3 rules of working with probability. Make a picture, make a picture, make a picture. So the most common kind of picture to make is a Venn diagram. Venn diagrams are really cool because we're going to do probabilities and we're also going to do conditional probabilities. And the Venn diagram really helps us organize things visually where we can see an overlap of probabilities. So when you roll 2 die, and I say, what is the probability of rolling a 7? Well, there's lots of different ways to roll a 7. I could have a 4 on the first die, a 3 on the second die. I could have a 2 on the first die, a 5 on the second die. I could have a 2 on the first die and a 5 on the second die. Like, there's a lot of combinations. 2 requirements for probability. Probability is a number between 0 and 1. You could think of it as a percentage, right? If I say 1 in 6, or 2 in 6, or 3 in 6, 3 in 6 would be 50%, okay? So our probability is always going to be a decimal between 0 and 1. 1 is 100% chance of the event occurring. I'll give you an example. If I say, what's the probability of flipping heads or tails on a quarter? Well, that's 2 possible events. So it'd be 2 out of 2, which would be 100%. I'm either going to get one or I'm going to get the other. So the probability assignment rule is the probability of the set of all possible outcomes in the trial must be 1. S represents the set of all possible outcomes. So we can, we're going to talk about sample space. The sample space, when we go to do Venn diagrams, and I will do a separate thing outside of this presentation with like real problems, and I'm sure you'll have some questions out of your homework that we'll discuss in class. But think of a piece of paper as being your sample space. And then we can organize the possible outcomes in the sample space, but the probability of everything in the sample space has to add up to 1. In other words, this is 100% of all the events or possible outcomes. Okay? So when you have a set of outcomes that are not in the event A, it's said or called a complement of A. So the complement of A is the complement. The probability of A plus the probability of its complement should always equal 1, or as they've listed it here, the probability of A is equal to 1 minus the complement, right? So if I have a 80% chance of something occurring, then I have a 20% chance of something not occurring. Does that make sense? All right. The addition rule, events have no outcomes in common. They are called disjoint or mutually exclusive. Okay? I have a bag that has 4 marbles in it, a blue, a yellow, a red, a green, and I have a die that I could roll. I'm never going to reach in the bag and pull out a 6. Does that make sense? I'm never going to roll blue, but I'm going to have a combination of the 2 in the sample space. So we would demonstrate or write this out by making the picture. This is still a Venn diagram. If A is rolling a die, I'd put 1, 2, 3, 4, 5, 6 in there. If B is choosing a color, I'd put red, blue, green, yellow, whatever the colors were. But those 2 events are mutually exclusive. One does not depend on the other. Okay? So if they're disjoint events or mutually exclusive events, the probability of one or the other occurs the sum of probabilities. So the probability of A and B are disjoint. So you could just add those probabilities up. What's the probability of me rolling a 2 and getting red? Well, it'd be 1 out of 6 or 1 over 6 plus 1 over 4, whatever that adds up to be. Okay. They are said to be disjointed or disjoint. Multiplication rule. If the 2 events are same scenario, except now I want to figure out what's the probability of both of them occurring. In other words, what's the probability of me getting a 2 and the probability of me getting a red in one trial, right? Like they're even though they're independent, I want to figure out the probability of getting that combination of 2 things. Well, here the math is a little different. We would multiply those 2 probabilities, okay? And I don't know if you guys remember this, but this is set notation. So this, let me go back here. Remember that this means or. This is a union. Do you guys remember that from Algebra 2 and Pre-Calculus? This little U means union. That means or. What's the probability of A or B? But this one here is what's the probability of A and B occurring? So there's 2 different formulas there. Okay? Here they say the word and. I don't agree with that. They probably should say or. But you can think of it as and. What's the probability of getting this and getting that? Or what's the probability of getting both in one trial? So anyway, so the multiplication rule then is if you have 2 independent events, they're not disjoint depending on the definition of what you're trying to do or what the outcome is. These two events have probabilities greater than 0. So you have set A, maybe you're rolling a die, you have set B, and you want to know what's the probability of them occurring together. So the event A and B is their intersection on the diagram. We'll talk about that in a second. Multiplication rule. Many statistics methods acquire an independence assumption, but assuming independence doesn't make it true. Always think whether that assumption is reasonable for using the multiplication rule. So we basically have two formulas, and we have to decide what is it that we're trying to make the prediction about. What is this probability being used for? If I just want to know the probability of getting a 2 or red, that would be one approach. If I want to know what's the probability of getting a 2 and red, that's a different type, right? So again, like I stated before, if you have a union, according to set notation and set theory, then that uses the word or, the probability of something or something else happen. And you wouldn't use the multiplication rule in that scenario, you would just add the probabilities up. But if I say, what's the probability of this and that occurring, then that's the intersection. And an intersection, you would use the multiplication rule. The clues is like when you get your homework, if it says, what's the probability of this or this occurring, you would use addition. If they say, what's the probability of this and this, you probably will use multiplication, but you have to be careful, okay? In most situations where we want to find a probability, we'll use the rules in combination. A good thing to remember is that it can be easier to work with the complement of an event that we are really interested in. So if I say, what's the probability of getting a 5 or lower when I roll one die? The complement of that would be to roll a 6. So I could take 1 over 6 and subtract it from 1, and that would give me the probability of all the other options. Okay? So beware of probabilities that don't add up to 1. That's the main thing. When you add all this stuff up, if it doesn't add up to 1, you messed up somewhere. Okay? To be a legitimate probability distribution, the sum of the probabilities for all possible outcomes have to equal 1, because that means 100% of the events could occur. So don't just add probabilities of events if they are not disjoint. Events must be disjoint to use the addition rule. Okay? Don't multiply probabilities if the events are not independent. The multiplication of probabilities of events that are not independent is one of the most common errors that people make with probabilities. Don't confuse disjoint and independent. Disjoint events can't be independent. Okay? So one of the things that we haven't talked about yet is a conditional statement. That's more like drawing cards. A conditional statement changes the probabilities because you're saying, what happens if I do this and I do that? Usually the word given is used in there, but we're just focusing on disjoint and independent. Okay? If I say, well, I'm not going to give you a scenario because I feel like I'll overload you. But anyways, what have we learned? We've learned that the probability is based on long-run relative frequencies. The law of large numbers speaks only of long-run behavior, but we may not be aware of all the behavior. Watch out for misinterpreting the law of large numbers. Just because you flipped 20 heads in a row doesn't mean somebody else in the world didn't flip 20 tails. So the probability is based on each time you flip that coin 50-50. There are some basic rules for combining probabilities and outcomes to find the probabilities for more complex events. There's a probability assignment rule. There's a complement rule. That's very helpful. The addition rule for disjoint events and the multiplication rule for independent events. The disjoint and independent are going to be the hang-up for you because there's two scenarios. Remember that the independent events will be two separate events but they will have an overlap or an intersection. Disjoint has no intersection. That's what disjoint literally means. Mutual exclusivity in a Venn diagram is two separate circles that do not overlap. Independent events are two separate independent events. In other words, the probability of one occurring doesn't have an impact on the other occurring, but they can overlap depending on how you frame the question. For the AP exam, for even the most simple probability problems, always show your work. It may even just be to show the fraction that you use to calculate the percentage. It could save you. All right, any questions? Okay, that's all I have for this today.